So yeah, recently we put out this work, so you can find it on the archive here, and also now to appear in Physical Review X. But before I go into what we've been working on, I think I want to give a bit an overview of some of the aspects of the strong coupling physics of the Hubbard model. So I guess everyone who has been following this lecture and the seminar series is by now very familiar with the Hubbard model, but for those who are maybe not, let's just quickly recap it. So the Hubbard model is a model of electrons, fermions, described by these operators, fermionic operators C, and they hop around on a lattice with a kinetic energy T. And when two electrons of the same side, of opposite spin, are on the same side, they experience a Coulomb repulsion. So this is a very simplified model of electron interactions, but it's relevant to a broad range of materials. And so a deciding factor in this model is the ratio between this kinetic energy and the interaction energy, U. And so often when one is talking about the Hubbard model, one can talk about different regimes. And okay, it's a matter of taste, but broadly one can distinguish between two regimes. So that's maybe a weak coupling regime, where the physics of metals and Fermi liquids is important. And there's a strong coupling regime, where the physics is more like being insulators, not insulators, and the accompanying antiferromagnets. Of course, that's a very coarse distinction, and here I say like weak coupling is maybe less than U/T than 2, and strong coupling larger than 6, but of course that's just a matter of taste, how you define it. So the defining property of the strong coupling regime is actually that this favors two electrons of opposite spin being on the same side. So that's kind of the most central feature at large U. And so what do we think that at large U this phase diagram looks like? So not only are the kinetic energy and the potential energy U parameters in this model, but of course the temperature is a parameter, but also the electron density order. And so this is shown here. So here I'm on the x-axis, I'm showing the hole doping, which is 1 minus the electron density. And so what do we believe the Hubbard model phase diagram as a function of those two parameters in a strong coupling regime might look like? Well, we think it might look like something similar to what is found in the cuprates. And so there in the cuprates, we have a lot of different phases. So this is only a toy sketch. But there is, of course, the very prominent superconducting, high TC superconducting phase. There's a normal metal. There's maybe this often discussed strange metal. But at half filling, so 1 electron per side, there's this antiferromagnet, which we are going to focus in this talk a little bit more. There's this pseudo-gap phenomenon, where so here I'm showing like ARPAS data taken from this picture. So we see that the Fermi surface is kind of gapped out at the boundary of the Brillouin zone, but it still remains gapless close to this nodal point. And we have these Fermi arcs developing. And so kind of the full Fermi surface is broken up in this regime, which is a yet to be understood problem. And so what else is observed in those cuprates? So what one can find when doing electron scanning tunneling microscopy, as done in this wonderful paper here, 2017, one can actually measure the local electron density in these copper planes of the cuprates. And this is what's shown here in this plot taken from this paper. And so we see that there are these regular density wave patterns. Yeah? And so this is what I'm calling stripes here. Okay, but before we go into a bit more detail, I think I want to give you some toy pictures, how I kind of understand the physics of strong coupling. So let's do a small introduction to what is called stripe physics in the hole-doped antiferromagnets. So let's consider the Hubbard model. We are at half filling, so that means there's 1 electron per side. And we take the limit of U/T to infinity. So that's the very strong coupling expansion. Well, what most people might know is if one does that, one ends up with an effective Hamiltonian, which is the Heisenberg Hamiltonian. So one has interactions between spins on neighboring sites, and this interaction strength is set by this energy scale J, exchange interaction, which is scales as T squared over U. And so the spins stay localized on a lattice, and they interact via the spin interaction. And so the fact, what's important to know is the sign of this J, so it's positive. So what does this mean? So the spins, they want to align in antiferromagnetic patterns. So if they were classical spins, they would like to align one spin pointing in some direction and the other spin pointing in the opposite direction. And so this is called antiferromagnetism. And so this is the pattern it would like to form at half filling in the strong coupling regime. Of course, if one adds quantum fluctuations and really treats this quantum mechanically, it's not a priori clear whether the ground state of such a system at low temperature or at zero temperature is actually an antiferromagnet. But that has been established by various methods, including spin wave theory and also numerics, mostly exact generalization. So now what does actually happen if we introduce holes to the system? And so there's this toy picture I want to show you. So here what I'm showing is I just leave out one electron in this pattern. And so leaving out this electron is this gray circle. And so it's not really an actual object, it's just the absence of an electron here. And so this hole wants to have a kinetic energy. So the Hubbard Hamiltonian also has this kinetic energy term. And this should be minimalized. So if this hole is hopping around, which actually means that this electron is hopping to the other side, what happens? So if this hole is hopping to the right, this electron has to hop to the left. So this means that here we have these three spins pointing in the same direction. And so of course this costs energy. They are not aligned antiferromagnetically. So this comes as an energy cost. And so if this hole wants to travel even further, this comes at a very high energy cost. So we see there's like all these spins pointing in the same direction. And so this comes at a very high energy cost. They are not aligned antiferromagnetically. Similar here, they are all pointing down. So there's a high energy cost of this. So how can this be actually remedied? Well, what we can do is these holes, they can kind of form pairs. And this was shown here. So if you do the same exercise again, and you move both holes to the right, what you see is, well, the antiferromagnetic pattern is not distorted at all, and we don't pay an energy penalty for this. So two holes together, they can kind of have a finite kinetic energy, and they can travel around freely. So we see it's actually energetically favorable for the holes to bind together. But now what happens if we even have more holes? Let's say we have 4 holes on this 4x4 geometry, and I'm just erasing like the electrons here. So if they want to move from the left to the right, what do we see? So I'm moving all these holes to the right, and we see that the electrons here are pointing both down and both up. And so this comes at an energy cost, of course. So there's an energy penalty for that. So having exactly the electrons being aligned in this way is not energetically favorable. But how do we remedy this? And the trick is very simple. One can actually switch the polarization or the direction this antiferromagnetic domain is pointing to. So if you compare this to this previous slide, here it would be up, down, up, down. But if the electrons, so if there's a line of holes and the electrons flip the sign of the antiferromagnetic domain, this is actually very much energetically favorable. So if those electrons hop to the right, we see there's no energetical cost coming with this. So we see whenever there's a maximum in the hole density, it's energetically favorable for the antiferromagnetic domain to reverse its polarization. And that is what is called the stripe order. So stripe order is being this intermixed order between yeah, well, this whole maxima in the whole density or this charge density waves, accompanied by being by the antiferromagnetism switching its polarization. And okay, well, these are very much toy pictures, but is there actually some physical relevance to this? Does this really happen? So what I've shown you here is, of course, all like a classical picture. We don't take the fermion anti-commutation relations into account, and we don't take any quantum fluctuations into account. So does this actually, the simple toy picture actually hold in reality? Well, it turns out it does in certain regimes. So so this stripe picture, to be fair, it has first been proposed within this Hartree-Fock approximation in the late 80s. So I think there were a couple more people who claimed this or proposed this, but here I'm citing those two papers. And so I think the first real evidence that these stripes are actually realized is the ground state of the Hubbard model came from DMRG simulations. And at that time, so this was done like in the late 90s then, after the invention of DMRG, so the algorithm Miles has been talking about before. This stripe physics was found in the TJ model. So this is like a large U over T limit of the Hubbard model at finite doping. So similar to the Heisenberg model, if we crank up U over T at finite doping, we arrive at the TJ model. And this is the results they had. So what they simulate is the TJ model on a kind of an cylindrical geometry. So the way this DMRG simulations work is one kind of wraps this matrix product states Miles has been talking about on this cylinder. So typically one has like open boundary conditions in the X direction and periodic boundary conditions in the Y direction. And so for this system here, the TJ model for a particular set of parameters, they computed the ground state and measured the magnetization as well as the local electron density. And this is shown here. So we see there's like this spin pointing down, up, down. So there's like antiferromagnetism. But then there's also this maximum in the hole density. So the diameter of those holes, that's actually the hole density. So 1 minus the electron density. So we see there's a maximum in the hole density and the polarization of the antiferromagnetic domain switches. So we see it's down, down here. And then again, this antiferromagnetic pattern continues until the next maximum in the hole density where it remains up, up. And so this was done for the TJ model. And so people often question like how relevant the TJ model is really for the Hubbard model physics. And so there's in the recent years, people have really pushed this with a lot of different methods to really nail down the ground state of the Hubbard model in a particular set of parameters. And the particular set of parameters people have been focusing on quite a bit is this one here. So people want to study the ground state. You are at a particular doping, 1/8, which is for the cuprates, maybe close to this optimal doping. You are at a particular interaction strength, which is in the strong coupling regime, U over T equals to 8. And okay, you don't have diagonal T prime hopping. You just have this, no diagonal hopping. So just hopping on a square lattice. And there's been like a really concerted effort, also mainly by this Simons collaboration on the many-body electron problem, which showed that the ground state in this regime is indeed forming stripes. So again, this is what's shown here. The green circles are the hole densities and the arrows are the magnetization. And we see whenever there's a maximum in the magnetization, in the hole density, the magnet spins point in the same direction. So here, down, down, up, up. And yeah, this has been like a concerted effort. So, and multiple numerical methods have actually established this. So I want to mention like there was DMRG, then there was like auxiliary field, quantum Monte Carlo. There have been IPEPS studies and also what is called a density matrix embedding theory and also various other methods. And they kind of converge to this conclusion that indeed at 0 temperature in a strong coupling regime at finite doping, the Hubbard model realizes stripe physics. And along another way, some other authors also found signs of stripe physics at finite temperature. So these authors here, Hong et al., they studied a couple of different parameters. So with elevated temperature, the same hole doping, slightly smaller U, and also having an additional T prime. And so again, they, in some sense, find similar patterns than was found in the ground state, without going too much detail into it. And so this brings me now to our recent work, where we studied stripes anti-ferromagnetism condition at the pseudo gap in the doped Hubbard model at finite temperature. And so this has been a collaboration with Jan Johe, Steve White, Antoine, and Miles Dunmeyer. So why do I think actually this tensor network and METS algorithms are so neat? Well, let's look at this phase diagram and discuss a little bit where some numerical methods are strong. So at half filling, the Hubbard model does not have a sign problem. So it can be very efficiently sampled using classical quantum Monte Carlo. And one particular variant, I think, which is, works very well, is this auxiliary field quantum Monte Carlo. And so this is, can cover large lattices on a broad range of temperatures. As we have seen, this DMRG is a very successful algorithm to study ground state properties. So this is this matrix product state technique that Steve White developed. And so it can cover the ground state phase diagram. However, DMRG is kind of limited to these cylindrical geometries. So it's not, often they are only performed on, yeah, so I think the record of establishing the ground state exactly is with 6 cylinders. So these methods have to push to get to larger cylinders. Then there's a broad range of methods, which I summarize as green function methods, for example, diagrammatic quantum Monte Carlo or cluster DMFT. Which can operate in the thermodynamic limit, so there's no finite size effect often for those. But for them, the challenge is to really reach low temperatures. And but again, those methods are also very successful, and I think there has been some really promising progress in the recent years. And so now, what is this METS technique? Well, we have now shown that we can apply this METS technique to study the Hubbard model over the full range of temperatures, with the caveat that we are, similarly to DMRG, limited to the cylindrical geometries. So let me reiterate, what is this METS method? So as Miles has described before, it's a decomposition of the density matrix into typical pure states. So one can write any expectation value at finite temperature as being the trace, E minus beta h of the operator. And this can then be decomposed into a classical sum of positive probabilities times expectation values of pure states. And so how is this done? Well, one has to define, of course, this pi and this pure states. And those are these minimal entangled typical terminal states. So this psi I are actually only an imaginary time-evolved product state. And this prefactor 1 over square root pi I, that's just a normalization. The pi I is given by this. And so the algorithm is to simply random sample the states psi I in a particular way. And so without further ado, I think I want to show you how these states look like for the on the system that we can now actually simulate. So again, we are on this cylindrical geometries here, what we've done at width 4. And we settled at the interaction strength U over T equal 10, and are the hole doping 1 over 16. And so now what is shown on these plots here? So let me explain. So we have here 3 different temperatures. So the upper panel is at a temperature of 0.3. The middle panel is at a temperature 0.1, and the lower panel is at a temperature 0.025. Okay, what are these individual symbols? So these black holes are, again, these black dots, they are, the diameter of the black dots is proportional to the hole density. So what we see at these 3 different temperatures is at high temperature, the holes kind of want to bunch together, but they don't really form any particular pattern. Yeah? So we can go through a couple of these random sampled states. If we go to lower temperatures, these holes, yeah, they still don't really form regular patterns. However, if we go to this lowest temperature, we find that actually these holes and the electron form these regular waves, yeah? Which is shown here. Then again, what I'm showing with these arrows is actually this spin correlation with respect to the central side marked by an X. So these spin correlations, again, tell us something about the magnetism. So what do we see here? So we see at high temperature, there's not really antiferromagnetic domains forming. So this can be seen in the, not only by following the patterns of up and down, but also in the color of these background squares. So the background squares is simply a color, whether it's red or blue, is simply the sign of the staggered spin correlation. So we see whenever it's down, up, down, the background color is the same color, here blue, but whenever there's like this spins pointing in the same direction, it changes its color to red. So what we see is at high temperature, there's not really this antiferromagnetic domains forming. This changes at this intermediate temperature. So we see there's a stronger tendency towards antiferromagnetism. For example, here we have quite a large antiferromagnetic domain at this intermediate temperature, 0.1. So we see at this temperature already the antiferromagnetism is building up. However, if we go to this lowest temperature, we really see the stripes emerging. So again, to reiterate, so the stripes, they have this density wave pattern. And whenever there's a maximum in the hole density, the antiferromagnetic domain switches its polarization. So this is what we see here. So we see a spin pointing up, down, up. Oh, there's a maximum in the hole density. So the spin is pointing up again. And the antiferromagnetic domain switches sign. And so we see at this low temperature, yeah, actually stripes are finally evolving. So we can, with this, we can kind of get a feeling what is the temperature needed for stripes to develop. And so while these pictures are a bit intuitive and supposed to give you an overview, we would also like to quantify this more. And for this, the thing we look at, of course, is structure factors. And so if you're talking about magnetic and charge ordering, it's instructive to look at the magnetic structure factor as defined here on the lower side, left-hand side, and the charge structure factor as defined here. And so what these plots show is, well, those structure factors at different temperatures. So that we actually compute this zero temperature result from DMRG, and the finite temperature results are these different colors. So now this width 4 cylinder, if we Fourier transform it in the y direction, it has actually a resolution of 4 discrete momenta. And so what's shown on the left is the magnetic structure factor evaluated at the ky momentum pi. So for example, this point here, 1.0, that's actually the pi ordering vector of the antiferromagnetism. And so what do we see? So we see that, okay, at high temperature, the order is kind of flat. But if we decrease the temperature to 0.1, we see that there's this peak at pi increasing. However, if we go to lower temperatures and eventually to the ground state, we see that this peak at pi is shifted inwards towards 7 pi over 8 and pi. And this is exactly the defining feature of the stripes. So this is exactly the feature that we have these alternating antiferromagnetic domains. So this shift from the pi peak to 7 pi over 8, this is indicative of the stripes. So we find at 0 temperature, the stripes are actually realized for this particular set of parameters. And similarly, on the right-hand side, we find that at low temperatures, there's this peak developing at pi over 4. And this is, yeah, nicely also converges towards the 0 temperature result, which is shown as this gray line in DMRG. And so these wave vectors are consistent with one another. If we go back, we see that the wavelength of the charge density wave is half the wavelength of the antiferromagnetic wave. So we see it makes sense that this is shifted by pi over 4 and this is shifted by pi over 8, since the wavelengths are double of one another. Yeah, one thing I would like to emphasize is that really here we nicely converge this low temperature results to the 0 temperature DMRG result, which is again shown in this gray line here. Now we can look at the temperature dependence of the structure factor. And what I'm showing you here is the temperature dependence of this magnetic structure factor on the left and the charge structure factor on the right for particular values of the ordering vector. So again, on the left, we have the magnetic structure factor, and in blue, I show the magnetic structure factor evaluated at pi pi. So pi pi is the ordering vector of the antiferromagnetism. And the red lines are the magnetic structure factor evaluated at 7 pi over 8 in pi. So what we see is these blue lines, they have this maximum around 0.1. So we see the onset of antiferromagnetism, but below a temperature of 0.05, we find that actually the dominant ordering vector is the 7 pi over 8. So we can kind of rather exactly estimate the onset temperature of the stripe physics, which I would say is around here 0.05 maybe. And so this is also reflected in the charge structure factor. Here again evaluated at this pi over 4 wave factor, which picks up at the same temperature, so 0.05 than the stripe antiferromagnetic order. One thing I want to comment on this plot is here, what I'm showing for the first time is like how we do convergence analysis of this MPS technique. So instead of calling it chi, as Miles has been doing in the previous slide, I call this bond dimension D max. And so this bond dimension of this matrix product state we use, we compare our results from 3 different bond dimensions. And we see actually they are nicely converged within the error bars. So both these results, maybe there's this peak is not fully developed at the smaller bond dimension in the antiferromagnetism. But in the rest of the results, we see that the results do not depend strongly on the bond dimension we use to simulate the system. So now what I would like to convince you is what we are kind of simulating is a cut through the cuprate phase diagram indicated here. So at low temperature, we see stripe physics. And at elevated temperature, we get into this pseudo gap regime. And so for this, let's first look at the thermodynamics. So here, what I'm showing you is the specific heat. I compare like at half filling, which is whole doping P equal to 0, and again our doping, which is 1 over 16. And again, we compare results from different bond dimensions, and we also again find that they are nicely converged within the bond dimension. Moreover, at half filling, as I've told you previously, there's this auxiliary field quantum Monte Carlo, which is exact. And so we can exactly compare our results to this AFQMC method. And it also agrees nicely. So what we see in the specific heat is at half filling with this quadratic behavior, which is expected for an antiferromagnet, and this broad peak around the temperature of 0.2. Now, if we dope the system, we see this peak kind of remains at the same position, but there's the shoulder in the specific heat developing at, again, this temperature around 0.05. Now we can also look at the magnetic susceptibility, defined like this. And so it looks like this. Again, here on the left-hand side at half filling, on the right-hand side at distoping. And so what we find is that the magnetic susceptibility develops a maximum at certain temperature, both at the half-filled case and the whole-doped case. And so such a maximum in the magnetic susceptibility is often taken experimentally as the onset temperature of the pseudo-gap regime. So let's recap this a little bit. So again, the pseudo-gap regime in the cuprates is characterized by the Fermi surface being gapped out at the boundary in the Brillouin zone and these gapless modes at close to the nodal point. And yeah, I think one finding is that whenever this occurs, there's a maximum in the magnetic susceptibility. So there's this T star, which kind of characterizes the onset of this pseudo-gap phase. So this is like the first indication that something similar might be happening in the Hubbard model. So we see this maximum in the magnetic susceptibility. But let's go for this key feature of the pseudo-gap phase. So is there actually some spectral suppression on the boundary of the Brillouin zone? And so this is what we want to kind of capture by looking at the momentum distribution function. So the momentum distribution function, whenever there's a Fermi surface, so a gapless mode, this momentum distribution function should have a discontinuity. So this is known by Luttinger. And so we evaluated the momentum distribution function both at 0 temperature and also at finite temperature. So at 0 temperature, it actually holds that the momentum distribution function should have a discontinuity. And whenever there's a gapless mode. And so what I'm showing here is, again, a cut through 3 lines, the Brillouin zone. So we are simulating this on a width 4 cylinder, which has a resolution of 4 discrete momenta in the y direction. And these are shown in the different colors. So whenever we are at ky equals pi, we plot green. So this is this line here. Whenever we are at ky pi over 2, we plot it in red. And ky equals 0 in blue. And so what we are looking for, if there were a Fermi surface, would be a discontinuity at t equals 0. But however, we do not really observe this. What we observe is that the slope is steepest in the momentum distribution function, close at the red line. So this is this line here. And it's steepest close to this nodal region. So this indicates that the gap is smallest close to the nodal region in the signal particle function. And we see the slope is much smaller than here, so which is the first indication that the gap might be larger at the boundary of the Brillouin zone. And also in the blue line, we don't see there being a big slope, which indicates a small gap in the single particle excitations. One can also look at this a little bit different. So one can look at the Fourier transform of the electron correlation, and we Fourier transform them only in the y direction of the cylinder. And what I'm showing you here is a result of this quantity here. And this is only shown at 0 temperature. And what I'm showing you is this correlator as a function of the distance between the 2 different sides. And so what is shown here is that at 0, ky equals 0 and ky equal pi, this electron correlation is decaying very quickly exponentially. Whereas at ky equals pi over 2, this is decaying rather slowly. This indicates a smaller gap. So we can now actually estimate those energy gaps precisely. And the way to do this is one can simply do this by computing ground state energies. So here I'm, for example, giving the formula for a spin gap, which is compute the ground state energy of a system with m+1 and m-1 particles, and subtract from it the ground state energy of the system with m and m particles. And so there are similar formulas for a single particle gap, which is if I add 1 electron, and the charge gap. So this is computed by adding 2 electrons or removing 2 electrons. And this is different for the Hubbard model. As we've seen before, adding 1 electron has its own problems and has a bit different energetics. than adding 2 electrons. So that's the differentiation between a single particle gap and charge gap. Then we can compute these ground state energies using DMRG and look at the value of those gaps. And this is shown here on the right-hand side. So whenever we compute gaps, it's a good idea to study this as a function of system size. So on the y-axis, we have 1 over L on the x-axis, and by L is being the length of the cylinder. And on the y-axis, I'm showing you the gap. Yeah. And so different colors are the different gaps. And so there's a charge gap shown in olive. There's this spin gap shown in blue, and there's the single particle gap shown in red. And so now what we find is, interestingly, that the charge gap actually vanishes. So there are gapless charge excitations. However, the single particle gap remains finite. So what is our conclusion? So on this cylinder, we think the gap of the single particle excitations, it's still sizable. However, it is smallest close to this nodal region. And we find there's no charge gap since scaling the charge gap with the length of the cylinder extrapolates exactly to 0. And so let me switch gear a little bit. So I hope this got you interested, that we can get some really nice new results on this Hubbard model. And so I want to spend a bit talking about some of the computational details, if you stay with me for a little bit.
So Alex, maybe just a sort of general question before you go more into the more details of the method. So basically, out of this work, there is some sort of general picture that emerges, right? That at higher temperature, one has commensurate correlations, spin correlations, and nothing in the charge, and that's the pseudo-gap regime. And then as one cools down, at some point, the incommensurate correlation and the charge density wave develops, and that's the stripe regime. That's basically the overall picture, right?
Yeah, exactly. Yeah. Mm-hmm.
Okay.
Right.
Okay, go ahead. Thank you.
Okay. So again, let's recap this METS method. So we need to sample this minimally entangled typical thermostates psi I, which are this imaginary time evolution of a product state. And so the key problem is actually to compute this imaginary time evolution. And as Miles has been explaining before, the way to do this is to use these tensor network methods. So we represent a big tensor, which has like d to the power of n coefficients, so where b being the number of local degrees of freedom, so which is 4 for the Hubbard model, n being the number of sites. So if you want to store all of these coefficients, this scales as d to the power of n, and it's of course a very big number. But if we represent this as a matrix product state with a certain bond dimension, E, the number of parameters scales as number of sites, linear, times D, so being the local dimension, 4, times the bond dimension squared. And so this is, of course, very favorable. So we get an exponential scaling in the number of sites down to a linear scaling. And so the key problem in getting this METS simulations to work is to perform this imaginary time evolution. So computing the state psi I of a product state. And so these time evolution algorithms for matrix product states, they have been researched for quite a while. So I think the first algorithms, they were actually proposed almost 20 years ago, how to do this. But the field has gotten quite some breakthrough in only the last years. And I think a very nice method, without explaining it in detail, is this time-dependent variational principle, which has been proposed by Juto Hegemann in its present form in 2016. And there's also some updates very recently which improved this. And if you want to get an overview how this imaginary time evolution methods work, I can recommend you a review article by Sebastian Peckel, which is in 2019, which compares all of these methods and gives you the pros and cons of them. So what we decided, due to some technical reasons, to end up doing is to combine different methods. And I'm not going to go into detail there, but it's a bit of an involved technique to get very accurate results. So we start off with a method which is called TEBD. So this is actually the method Miles has been explaining, called time evolving block decimation, up to a certain initial time, and then switch to this time-dependent variational principle for the expert, first in a two-side scheme and then in a one-side scheme. And so we have to benchmark how well this works. And so I'm taking the chance to present some results I personally really like, but yeah, maybe it's a bit for experts. Okay, anyway, so what we want to do is to compute this imaginary time evolution. And this TDBP algorithm, it has two main parameters. So similar to time integrators for differential equations, you have a time step size. So it's the length of how much I step within one time step. The second parameter is the cutoff. So this is related to doing singular value decompositions of the matrix product states in this algorithm. And so what we did is to compare this to the states we developed by time evolution to exact diagonalization. And so if you want to compare to exact diagonalization, of course, we have to stay on smaller lattices. So here, what I did, I computed the time evolution of two different states, first at half filling and then with two holes on a 12-side lattice. So those are the states shown here. And what is shown on the right-hand side is actually the accuracy, how accurate we can get those time evolution. And I think this is really nice. So it's on the left-hand side, we always are at half filling. So time evolving this state. On the right-hand side, we are time evolving hole doped state with two holes. And the upper panels are at the temperature 0.1 and the lower panels are at the temperature 0.02. So what is plotted on the x-axis is actually the time step size, tau, on the log scale. So we did it over a range of sizes for this tau. And what's shown on the y-axis is this defect delta, which is 1 minus the overlap of the MPS time evolved state with the state from exact diagonalization. So we have this control parameter tau here and this control parameter epsilon, which are the different colors. And we see something remarkable. So if we increase this control parameter, we get very accurate results. So this defect is here for this parameter, for example, it's accurate up to 8 digits. And I think this is some rather remarkable precision. And even for these lower cutoffs, we get like six digits precision. So this is like on the level of being in single precision. So it's almost like machine precision, if you want to call single precision machine precision. Yeah, nevertheless, what's kind of surprising is that we can take this long time step sizes. So here we think that the optimum is mostly at the time step size of 0.5. So this is maybe a bit surprising for people who are used to, if you decrease the time step size, it becomes more accurate. Well, if you decrease the time step size, you have to do more cutoffs, so it becomes less accurate. So it's a bit different than, for example, solvers for ordinary differential equations. Yeah, and so this is actually the kind of parameters we did the simulations with. And not only did we do this convergence analysis, so in this work, we actually compared to quite a lot of other methods. So for example, at half filling, that's the obvious test. We can compute with auxiliary field quantum Monte Carlo. We can compare the spin correlation functions shown here at different temperatures with AFQMC, which are the gray boxes, and we see perfect agreement. We can compute the energy as a function of temperature. Again, we get a very nice agreement. And similar test, we can simulate this on smaller lattices. So we can simulate this on a 4x4 lattice using exact diagonalization. And also here, what I'm showing is the magnetic susceptibility. We have also perfect agreement with this exact diagonalization results, an extension of one I call DPQ. So this is also valid, especially at the doped case, which is not captured by AFQMC. And finally, what we added recently is a validation with a very nice and interesting point where there have been these quantum Monte Carlo simulations at finite temperature, finite hole doping, and also at T prime at a slightly lower U. And so this was this work I was mentioning before, where Wang et al. Who find signatures of the stripe phase of this incommensurate spin correlations at finite temperature, and we can kind of exactly reproduce their results without going into too much detail. So for example, here in the lower panel, I'm showing the density on a cylinder of length 16, and it exactly compares with their results here. So for example, this small dip also presented by them. But also these spin correlations, which are shown here in some way, match exactly what they have found. Okay, yeah, with this, I think, let me summarize. So in this work, this was the first application of the METS algorithm to simulate this 2D Hubbard model at finite temperature. And so admittedly, we are still stuck at this kind of cylindrical geometries here of width 4. However, what we can do is actually capture the full range of temperatures and essentially also go to the ground state limit, T = 0, which is captured by this DMRG method. We established the onset temperature of the stripes and find this antiferromagnetism in the pseudo-gap regime. We find also that this single particle gap is actually smallest, close to the nodal point. And we observe this vanishing charge gap. And yeah, with this, I think I would like to give you a little bit of an outlook, what we would like to do in the future. So I think this method is very promising, and the obvious thing to do is to further explore more what we can say about the cuprate phase diagram. So we see there's a lot of interesting phases we can now try to understand using this method. And so we would like to find out, maybe we can find out what is the onset temperature of the superconductivity in the system, if there is superconductivity, or at what parameters we can't find superconductivity. We can find out something about this transition from this pseudo-gap metal to this normal metal, and maybe also find something out about the strange metal regime here. And so I think what's important to do is to also work together with other numerical methods to kind of find agreement. And so there has been one project, I think we've been doing this very nicely, which is on the triangular lattice Hubbard model, where we kind of reached a handshake between different models. So here we've been combining all of those methods I've been talking about, the agrammetric Monte Carlo, cluster DMFT, DMFT, and yeah, also METS, to simulate the triangular lattice Hubbard model at finite temperature. And also here, we, for example, at this plot I like very much, so we bring all of those methods together. We simulate the potential energy and our broad range of interaction strength U over T. We actually find perfect agreement with some differences here in this intermediate regime, or slightly strong coupling regime. Okay, and yeah, with this, I think I'm done. So thank you very much for your attention. And yeah, well, thanks a lot to all my collaborators on this project. So Jan Johe, who was responsible for doing the auxiliary field, Quantum Monte Carlo, and of course, Steve Wyatt, my student Meyer, and Antoine Georges. So thank you very much.
Thank you very much, Alex, for this really beautiful talk. Overview of both physics and some technical advances. So that was a nice balance.